Hello friends, welcome to my lecture on review of Z transforms. This second lecture on review of Z transforms. We know that the Z transform are the discrete analog of Laplace transforms and they are used to solve difference equations. So, when we are given a difference equation, we take the Z transform of both sides of the difference equation and then solve the resulting algebraic equation for Z by n and then find the inverse Z transform to find the sequence by n. A formula for inverse unilateral Z transforms can be written as by n equal to 1 over 2 pi I integral over C Z by n Z to the power n minus 1 dz. Now, let us see how this formula has been derived. We know that Z by n is equal to sigma n equal to 0 to infinity by n Z to the power minus n. So, this is equal to by naught plus by 1 Z to the power minus 1 by 2 Z to the power minus 2 and so on by n Z to the power minus n and so on. Now, when you multiply this equation by Z to the power n minus 1, what you get? Z to the power n minus 1 into Z by n equal to y naught Z to the power n minus 1 plus by 1 Z to the power n minus 2 by 2 into Z to the power n minus 3 and so on. We get by n into Z to the power minus 1 and so on. The right hand side here is the Laurent series. In the Laurent series, the coefficient of 1 by Z gives the residue of Z to the power n minus 1 Z by n. So, residue of Z to the power n minus 1 into Z by n at Z equal to 0 is equal to y n. Okay. Now, by residue theorem, integral over C, where C lies in the region of convergence of this Z transform, okay, Z of y n, in the region of convergence of Z by n. If C is a simple closed curve, okay, or that is then integral over C Z by n Z to the power n minus 1 Z by n dz equal to 2 pi I into residue at Z equal to 0 of Z to the power n minus 1 Z by n. Okay. So, this is equal to 2 pi I into by n, okay, and hence by n is equal to 1 over 2 pi I integral over C Z to the power n minus 1 Z by n dz, where C lies in the region of convergence of Z by n. So, this is the inversion formula for the Z transform using calculus of residues. Now, here you can see this is the region of convergence, okay. In the region of convergence, this is a simple closed curve. So, which is an integral taken over a closed contour in the anti-clockwise direction in the region of convergence of Z by n as shown here in this figure. Now, let us use the inversion integral method to find the inverse Z transform of 3Z over Z minus 1 Z minus 2. We can see that here say by Z equal to 3Z, or here we are let us take instead of by Z, let us take uz. So, uz equal to 3Z over Z minus 1 into Z minus 2. Okay. Now, uz has simple poles at Z equal to 1 and Z equal to 2. Okay. So, the region of convergence here will be mod Z greater than 2. Okay. Now, let us see, we have the residue, let us find residue of Z to the power n minus 1 into uz at z equal to 1. So, this is residue of z to the power n minus 1 into 3z over z minus 1 z minus 2 which is equal to limit z tends to 1 z minus 1 into z to the power n minus 1 3z divided by z minus 1 z minus 2, because uz has simple pole at z equal to 1. So, this z minus 1 will cancel, and when z tends to 1 you get 1 to the power n minus 1 into 3 into 1. So, we get 3 divided by 1 minus 2. So, minus 1. So, it is minus 3. Okay. And then then let us find the residue of uz into z to the power n minus 1 at z equal to 2. So, this is limit z tends to 2 z minus 2 into uz is 3z divided by z minus 1 z minus 2 into z to the power n minus 1. Okay. So, z minus 2 will cancel, and when z tends to 2 you get 3 into 2 into 2 raised to the power n minus 1 divided by 2 minus 1. So, this is 3 into 2 to the power n. Okay. Now, so we know that we have found the residue of z to the power n minus 1 uz at z equal to 1, it is minus 3, and we have found the residue of z to the power z to the power n minus 1 into uz at z equal to 2. Okay. Now, let us go to the theorem. Theorem says that then by n equal to sum of residues. Okay. So, sum of residues is equal to, hence by n is equal to sum of residues of z to the power n minus 1 into uz at z equal to 1 and z equal to 2. Okay. So, this is equal to, we have minus 3. So, minus 3 plus 3 into 2 raised to the power n. Okay. So, by n is, this is for n greater than or equal to 0. So, we get this sequence 3 into 2 to the power n minus 3, 3 into 2 to the power n minus 3, 3 into 2 to the power n minus 1. Okay. So, this is how we get the inverse Z transform here using the inversion integral method. Let us take one more example here. Here you can see that this is uz. Okay. So, uz, this is uz. Okay. And uz has 3 poles. Okay. Z equal to 1, z equal to I, and z equal to minus I. Okay. So, we find similarly the poles lie at z equal to 1, z equal to I, z equal to minus I. Okay. All these poles lie on the unit circle, on this unit circle. Okay. Mod z equal to 1, the z equal to 1 here, z equal to I here, and z equal to minus I here. Okay. So, region of convergence here for this Z transform will be mod of Z greater than 1. Okay. And we will find these residues, residue at Z equal to 1 of uz into z to the power n minus 1 plus residue of uz into z to the power n minus 1 at z equal to I, and then residue of uz into z to the power n minus 1 at z equal to minus I. So, then un will be the sum of the residues of uz into z to the power n minus 1 at z equal to 1, z equal to I, and z equal to minus I. Z equal to minus I. So, we know, we have seen just now how to find the residue at a simple pole. suppose we want to find the residue at z equal to 1, then you multiply uz into z to the power n minus 1 by z minus 1. Z minus 1 will cancel with the z minus 1 in the denominator of uz, and then you take the limit as z tends to 1. So, we get the residue at z equal to 1, and similarly we can find the residue at z equal to I n minus I. Then the sum of the residues at 1 I n minus I will give you the desired inverse Z transform, which is the sequence u n. Now, let us go to find the inverse Z transform of Z cube minus 20 Z over Z minus 2 whole cube into Z minus 4. Now, here you can see we have a pole of order 3 at Z equal to 2 in the denominator, and a pole of order 1 at Z equal to 4. So, if this is uz, let uz, so this is equal to, let us say this is uz, okay, then uz has a pole of order 3 at z equal to 2 and a simple pole at z equal to 4. Okay. So, we will find the residue of z to the power n minus 1 into uz, okay, at z equal to 4, which is a simple pole. This will be limit z tends to 4 z minus 4 into z to the power n minus 1 into uz. uz is z cube minus 20 z divided by z minus 2 whole cube into z minus 4. So, you can see z minus 4 will cancel. Now, we can find the limit as z tends to 4. So, 4 to the power n minus 1, and then we have 4 cubed, which is 64 minus 80 divided by 4 minus 2 cube. So, that is 2 to the power 3, which is 8. Okay. So, 4 to the power n minus 1, here we have minus 16 divided by 8. So, this is minus 2 into 4 to the power n minus 1. So, we have found the residue at the simple pole z equal to 4. Now, we will have to find the residue at z equal to 2 of z to the power n minus 1 uz. So, here we have a pole of order 3. So, we know that the residue in case of a pole of order more than 1 is found by using this formula, residue of f z. Let we have this formula at z equal to, suppose z naught. This the formula is 1 over m minus 1 factorial limit z tends to z naught dm minus 1 over dzm minus 1 z minus z naught to the power m into fz. This is the formula for the residue in case fz has a pole of order m at z equal to z naught. So, here we have z to the power n minus 1 into uz, which is the function having a pole of order 3 at z equal to 2. So, this will be equal to 1 by 3 minus 1 factorial, that is 2 factorial, limit z tends to 2, okay, z naught is 2 here, then d square over dz square, okay, and then we have z minus 2 raised to the power 3 into z to the power n minus 1 into uz, which is z cube minus 20 z divided by z minus 2 whole cube into z minus 4. Okay. So, this z minus 2 whole cube will cancel. Now, we have to differentiate z to the power n minus 1 into z cube minus 20 z divided by z minus 4 twice with respect to z, take the limit as z tends to 2 and then multiply by 1 by 2 factorial, that is half. We will get the residue at z equal to 2, and then we add to this residue the residue which we have already found at z equal to 4. We will get the required answer. So, inverse unilateral Z transform. Now, there are other inversion methods. Let us say if z by n is a rational function, okay, then how we will find the inverse z transform. So, if z by n is a rational function, that is it is a ratio of two polynomials, say b naught plus b 1 z and so on b m z to the power m divided by a naught plus a 1 z and so on a p z to the power p. Then one method is that direct long division method. Okay. It is a straightforward but not entirely practical method. In this method we obtain a power series expansion for z by n from the rational expression, and then from the definition of z transform the terms of the sequence can be identified one at a time. Let us say z by n is z over z minus a. So, what do you do? This is your z, you are dividing z by z minus a. So, it will go 1 times, so z minus a. So, we will have minus plus here z, so this will be a. Now, then we will take, we have to make this a 0. So, we multiply a by z. So, a by z, when you multiply to z minus a, you get a minus a square by z. Okay. So, this will cancel, now you have a square by z. Okay. So, in order to cancel this a square by z, we have to multiply by a square by z square. So, we get a square by z minus a square by z square. This cancels and we get now a square by z square, and to cancel a square by z square, now we multiply a square a cube by a square by z. Here we, this will be a cube by z square, a cube by z square. So, now we will have to multiply by a cube by z cube, a cube by z cube, then this will be a cube by z square minus a 4 by z cube, and we get a 4 by z cube and so on. Okay. So, we get the series 1 plus a by z plus a square by z square plus a cube by z cube and so on, continuing this division method. Okay. Now, you can see this is 1 plus a by z plus a square by z square plus a n by. So, this is nothing but sigma n equal to 0 to infinity a by z raised to the power n, okay, or sigma n equal to 0 to infinity a to the power n into z to the power minus n. So, this is the z transform of a to the power n. So, by n is equal to a to the power n. So, it is not a practical method because we can do this only for a finite number of steps, and it is sometimes very complicated. Now, let us find the inverse z transform of z over z plus 1 whole square, say for example. So, z over z plus 1 whole square is z over z square plus 2z plus 1. Let us do the same thing as we did in the previous example. So, we have z over z square plus 2z plus 1. Okay. So, we have z divided by z square plus 2z plus 1. Okay. So, we will multiply this z square by 1 over z. So, that we have here z square into 1 by z as z, then 2z into 1 by z is 2, then plus 1 by z. When we subtract, we get minus 2 minus 1 by z. Okay. Now, we want to cancel minus 2. So, we multiply by minus 2 over z square. So, we get minus 2, then minus 2 over z square into 2z. So, we get minus 4z over z square. So, minus 4 by z, okay, minus 4 by z minus 2 by z square. So, this cancels, 4 by z minus 1 by z is 3 by z, and then we get plus 2 by z square. So, now in order to cancel 3 by z, we multiply by 3 by z cube. So, we get 3 by z here, then we get 2z into 3, that is 6z by z cube. So, 6 by z square, then we get 3 by z cube. So, this is minus 4 by z square minus 3 by z cube. Now, in order to cancel minus 4 by z square, we will have to multiply by z square we have to multiply by 4 by z to the power 4 minus 4 by z to the power 4. Okay. So, we can see this is nothing but 1 over z minus 2 over z square, okay, 3 over z cube minus 4 over z to the power 4 and so on. This we can write at sigma n equal to 1 to infinity sigma n equal to 1 to infinity z to the power minus n minus 1 to the power n minus 1 into n. Okay. So, if you take n equal to 1 you get z to the power minus 1, when you take n equal to 2 you get minus 2 into z to the power minus 2, and then you take n equal to 3 you get 3 over z cube and so on. So, thus we have thus u n here is equal to 0 when n is equal to 0 and it is minus 1 to the power n minus 1 into n when n is greater than or equal to 1. So, you can see here this u n is 0 when n equal to 0 and when n is greater than or equal to 1 u n is minus 1 to the power n minus 1. Now, inverse z transform by partial fraction. Okay. So, x z is b naught plus b 1 z plus say and so on b m z to the power m over a naught a 1 z plus a p z to the power p, where m is less than p, and the roots of the denominator polynomial are z r k k equal to 1 to p. When the r k's are distinct and simple, then we can write x z as sigma r k equal to 1 to p a k over z minus r k. Okay. So, since r k's are distinct, okay, the a k can be found out directly. A k will be equal to z minus r k into x z at z equal to r k. Okay. So, we know the value of a k's now. Now, what you do in order to find the inverse z transform x z, inverse z transform of x z, what we do is we have to bring it to the standard form, the right hand side to be in the standard form. We know that z transform of a to the power n equal to z over z minus a, where mod of z is greater than mod of a. Okay. So, z inverse of z over z minus a will be equal to a to the power n. Okay. Now, so what we will do, we will write x z as sigma k equal to 1 to p z inverse into a k z divided by z minus z k. Okay. And then apply the inverse z transform, z inverse of z over z minus r k equal to r k to the power n by using this formula. Okay. Now, let us apply the delay property. The delay property says that if z transform of x n is equal to x z, then z transform of x n minus k, x n minus k equal to z to the power minus k x z. Okay. So, inverse z transform, when you take inverse z transform of x z, okay, this will give you the sequence action. So, this will be sigma k equal to 1 to p inverse z transform a k is we can write, then inverse z transform of z inverse into z over z minus z k, z over z minus z k. Let us write z over z minus z k here, z minus r k. Z minus r k. Okay. So, this will be sigma k equal to 1 to p a k into z. Now, we apply this property. You see, so this is this says that Z inverse, if you take the inverse Z transform, this will imply that x n minus k equal to Z inverse Z to the power minus k x z. Okay. So, take k equal to 1. So, this will be z over z minus r k has transform inverse Z transform as r k to the power n, and when we multiply by Z to the power minus 1 here, n is replaced by n minus 1 here. So, we have r k to the power n minus 1. Okay. So, using this delay property, this one, okay, Z transform of Z inverse of Z inverse into Z over Z minus r k is equal to r. So, r k to the power n minus 1. Okay. So, we get here a k r k to the power n minus 1 u n minus 1, because here you have you can multiply this by u n also. So, u n minus 1. Okay. This is x n k, x n minus k u n. Into u n. Okay. So, this will become actually u n minus k, sorry, u n minus k. So, this will be r k to the power n minus 1 u n minus 1 in k equal to 1 to p in view of this property. So, we have this property we write here, the property that I have written here, x n minus k u n minus k equal to Z inverse. So, this property we apply. So, Z of by n minus k u n minus k Z to the power minus k by Z, using this property, this inverse Z transform of this will give you x n equal to sigma k equal to 1 to p a k and Z inverse of Z over Z minus k. Okay. Will give you r k to the power n minus 1 u n minus 1. So, this is how we can find the Z transform. Now, let us say for example, by Z equal to Z minus 1 over Z minus 2 Z minus 3. When you break it into partial fraction, you get by Z equal to minus 1 over Z minus 2 plus 2 over Z minus 3, and you know that a to the power n goes to Z over Z minus a when we take the Z transform. Okay. So, by the inverse Z transform of by Z will be Z inverse of by Z, as we have just now done by using the delay property. So, Z inverse of minus half minus 1 over Z minus 2, okay, plus 2 times Z inverse of 1 over Z minus 3. Okay. So, we can write it as Z inverse of minus we can write outside, okay, then Z inverse into Z over Z minus 2, and here we have 2 times Z inverse of Z over Z minus 3. Now, Z transform of a to the power n is Z over Z minus a. Okay. Then Z transform of by n minus k u n minus k is equal to Z to the power minus k by Z. Let us apply this property. So, then k is equal to 1 here, okay, k equal to 1 here. So, Z inverse of Z into by Z will be equal to by n minus 1 u n minus 1. Okay. So, here 2 to the power n is the Z transform of 2 to the power n is Z over Z minus 2. So, we will get this as Z inverse by Z will be equal to minus 2 to the power n minus 1 u n minus 1 plus 2 times 3 to the power n minus 1 into u n minus 1. Okay. So, this is nothing but you can write it as minus 1 by 2 into 2 to the power n u n minus 1 plus 2 by 3 into 3 to the power n u n minus 1. Okay. Now, u n minus 1 is 0 when n equal to 0. So, at n equal to 0 by n is 0, and when n is greater than or equal to 1 u n minus 1 is equal to 1. So, you get this answer. Okay. Now, determine the inverse Z transform of z over z minus 1 z minus 3 whole square. Now, what we do here, we can write by z over z. Okay, by z over z, there is another technique where we write the partial fractions of by z over z. By z over z will be equal to 1 over z minus 1 z minus 3 whole square. When you break it into partial fractions, you get this, this and these are the partial fractions. Now, then after we have got the partial fractions, we multiply z both sides. So, this will give you by z equal to z over 1 by 4 z over z minus 1 minus 1 by 4 z over z minus 3 and then 1 by 2 z over z minus 3 whole square. Okay. So, inverse Z transform will give you by n sequence. By n will be equal to 1 by 4 1 to the power n, okay, then minus 1 by 4 3 to the power n, and then here now let us see, let us recall that Z transform of n a to the power n is a z divided by z minus a whole square. So, we have to use this one. Okay. So, inverse Z transform of az upon z minus a whole square equal to n a to the power n. Okay. Now, here we have z over z minus 3 whole square. Okay. We have to take the inverse Z transform of this. So, we write 1 over 2 into 1 over 3 and here we can make it 3 z over z minus 3 whole square. So, when you bring it to this form, inverse Z transform of this, okay, we can find. We write it in the standard form. To do that, we get 1 by 2, 1 by 3 and then Z inverse of this. Okay. So, then 1 by, so the inverse Z transform of this then will be equal to n into 3 to the power n. So, we have 1 by 4 1 to the power n minus 1 by 4 3 to the power n, then 1 by 6 n times 3 to the power n. Okay. So, we get this 1 by 4 minus 1 by 4 3 to the power n plus 1 by 6 and 3 to the power n. Now, if u z is expressed in the power series method, we express u z in the form of a power series and then take the inverse Z transform. Now, let us consider this log z over z plus 1 by and we find the inverse Z transform of this by power series method. So, we can write log z over z plus 1 as we can write log z over z plus 1 equal to minus log 1 plus by if by we take as 1 over z. Now, we know that log of 1 plus by can be expanded in a power series in if mod of by is less than 1. So, we can write this as minus by square by 2 plus by cube by 3 minus by 4 by 4 and so on, provided mod of by is less than 1. Okay. Now, let us replace by 1 over z. So, we get minus 1 over z plus 1 over 2 into 1 over z square minus 1 over 3 into 1 over z cube, okay, like this 1 over 4 1 to 1 over z to the power 4 and so on, okay, and where mod of z is greater than 1. Okay. So, here we can see that the un, okay, if let us take this as u z. So, u1 equal to 0 when n is equal to 0, okay, and when n is equal to 1, 2, 3 and so on, it is minus 1 to the power n divided by n. Okay. If you take n equal to 1, u1 is minus 1, u2 is 1 over 2, u3 is minus 1 over 3, u4 is 1 over 4 and so on. So, this is how we can find the inverse Z transform by expanding log Z over Z plus 1 in the form of a power series. Now, using we have in the previous lecture discussed the convolution theorem. We can use convolution theorem here to determine the inverse Z transform. So, we know that Z inverse of Z over Z minus A, this is equal to A to the power n, and Z inverse of Z over Z minus B is B to the power n. Okay. So, then by convolution theorem, Z inverse of Z square over Z minus A, Z minus B, product of this and this, let this be u z, this be v z. So, Z inverse of u z into b z is equal to convolution of u n b n. So, A to the power n convolution with b to the power n. Okay. And by definition of convolution of two sequences, we get this as sigma m equal to 0 to n A to the power m into b to the power n minus m. Okay. So, this is equal to b to the power n can be written outside, and we get sigma m equal to 0 to n A by b raised to the power m. Okay. So, this is the geometric series. So, we can write b to the power n, then we have A by b raised to the power n plus 1 minus 1 divided by A by b minus 1. Okay. So, this will be equal to if we calculate this, this will be equal to b to the power n A to the power n plus 1 minus b to the power n plus 1 divided by b to the power n plus 1 into A minus b divided by b. Okay. So, this cancels with this, you get b here, and b cancels with this b here. So, we get A to the power n plus 1 minus b to the power n plus 1 divided by A minus b. Okay. Now, let us find the solution of the difference equation. So, we have the difference equation by n plus 2 minus 3 over 2 by n plus 1 plus 1 over 2 by n equal to 1 by 3 to the power n u n. U n is the unit step function, by naught is equal to 4, by 1 equal to 0. So, let us take Z transform of the this given equation. So, Z transform of by n plus 2 minus 3 by 2, we are using linearity property when we are writing the Z transform of the left side. Okay. So, 3 by 2 Z of by n plus 1 plus 1 by 2 Z of by n equal to Z transform of 1 by 3 to the power n u n. Okay. Now, let us use the advanced property. Advanced property we discussed in the previous lecture. It says that Z of by n plus k equal to Z to the power k into by Z minus by naught minus by 1 by Z and so on by k minus 1 over Z to the power k minus 1. Okay. So, here by Z is the Z transform of by n, by Z equal to Z transform of by n sequence. So, here when you write the Z transform of by n plus 2, let us use this advanced property. So, take n equal to 2. So, we get Z square, inside the bracket we get by Z minus by naught, and then we get k equal to 2. So, we get by 1 by Z. Okay. Then minus 3 by 2 we get Z of by n plus 1, again we use the advanced property. So, we get here Z times by Z minus by naught, okay, plus 1 by 2 Z of by n we take as by Z. Right hand side u n is equal to 1 for all n greater than or equal to 0. So, we need the Z transform of 1 by 3 to the power n, which is Z over Z minus 1 by 3. Okay. Now, by naught is equal to 4, by 1 equal to 0. Okay. So, putting the values of by naught and by 1 and simplifying this equation, we will get the value of by z. Okay. So, z square by z will be the coefficient of by z is by z times z square minus 3 by 2 z plus half. Okay. By naught we put as 4. Okay. So, we get minus 4 z square, here y naught is equal to 4. So, we get minus plus 6 z. So, minus 4 z square plus 6 z. Okay. This term is 0 because by 1 is 0, and then it is equal to z over z minus 1 by 3. Okay. Now, we can simplify this and we get by z as 24 z cube minus 44 z square plus 18 z divided by 6 z cube minus 11 z square plus 6 z minus 1. Okay. Then as we have discussed earlier, we write by z over z. Okay. Because 6 z cube minus 11 z square plus 6 z minus 1 has simple roots, z equal to 1, z equal to half, z equal to 1 by 3. So, writing by z over z, we will this by z over z we will then factorize. Okay. By z over z will be 24 z square minus 44 z plus 18 divided by 6 z cube minus 11 z square plus 6 z minus 1. So, you divide by 6 in the numerator and denominator, and the coefficient of the denominator here coefficient of z cube we make as unity. Okay. So, after you make the coefficient of z cube unity here, its factors will be z minus 1, z minus half, z minus 1 by 3, and the corresponding partial fractions are minus 1 over z minus 1, minus 4 over z minus half, plus 9 over z minus 1 by 3. Now, you multiply by z. Okay. So, by z equal to minus z over z minus 1 minus 4 z over z minus half plus 9 z over z minus 1 by 3, and then you take the inverse z transform. You will get by n equal to minus inverse z transform of minus z over z minus 1, that is we have minus 1, then minus 4 times inverse z transform of z over z minus half, which is minus 4 into 1 by 2 to the power n, and then plus 9 times inverse z transform of z over z minus 1 by 3, which is 9 times 1 by 3 to the power n. So, this is how we solve this difference equation. When we want to solve a difference equation, we take the z transform of the difference equation. The left hand side, when we write the z transforms, we use the linearity property and the advance property. The advance property, and of course, sometimes we need delay property also. So, we use the advance property or the delay property to get the z transform of the difference equation. Then we solve this for by z. Okay. By z is a quotient of two polynomials. Okay. When we have by z as a coefficient of two polynomials, we factorize the denominator, see its factors. If the factors are linear, okay, we write by z over z, that is we divide by z, and then the by z over z expression is factorized into simple factors. This after we have got the fractions of by z over z, then we multiply by z to get the value of by z, and then once by z is obtained, we take the inverse z transform. Okay. Keeping in mind that inverse z transform of z over z minus a is a to the power n, will lead you to the solution of the given difference equation. Now, if in the denominator you have the a factor occurring more than once, okay, say if it occurs more than once, say it occurs twice, okay. So, then you have z minus a whole square in the denominator. Suppose you get z minus a whole square in the denominator, okay. Then we will need to use that formula z transform of n a to the power n equal to a z upon z minus a whole square. We will need to use this formula. So, here also we will write by z over z, and then we will write the partial fractions. We multiply by z. When we will multiply by z, the partial fraction corresponding to the z minus a square factor will have z over z minus a whole square. Okay. So, inverse transform will be easy to find. It will be n a to the power n divided by a, that is n times a to the power n minus 1. Okay. If z minus a occurs thrice, then we will need to use z transform of n square a to the power n, because when you take the z transform of n square a to the power n, there you get z minus a whole cube in the denominator. So, that is how we find the inverse z transform of the once we have solved for the given difference equation for by z, and we get the solution of the difference equation. So, thank you very much for your attention.